Now we are going to hear from Emanuele Viterbo on DNA storage. I'm excited. Eitan got us set up a bit for DNA storage. We can hear a bit more.
I'll bank on Eitan's help a bit. Okay, good. So, thank you for this picture and for inviting me, of course. So I'll just tell you, I started doing some things on DNA when a startup company asked me to design DNA tags for tagging objects against counterfeit. So that like 5 years ago. So then the good thing happened is that I didn't know anything about DNA, but I kind of got the data from this, so I kind of learned the enough biology, not much, but enough to get to this level today. Now, as Eitan said this morning, their DNA storage is quite active. There is a DNA alliance, and then in order to join, you needed to have a name. So we had to think hard of a name, and we called this team, the 2 students and a postdoc, we were working on this, the DNA squiggleism. And you will see, because squiggles are the signals that you are actually processing to sequence DNA. So I'll show you later some pictures, but quickly over this. It's a tape with 4 states, which are the nucleotides, and they come in pairs, and basically half of the double strand is enough because the information on the other half is kind of a mirror copy of that. Again, if you take it as a tape, it's enough to start off with. But then as you go, you learn more. Ask questions maybe.
Isn't part of the robust, the whole part seems right in there, right? One is robustness, that it's extremely robust. But doesn't part of the robustness come from the fact that in bodies there are actually pairs?
Yes. It's stable. So when it's paired, it's extremely stable. When you break it up in 2 parts, it's less stable.
What we heard from now, it seems that they're not actually pairs. They're just single sequences, or does it automatically become a pair?
So it's double-stranded DNA is the helic. So the previous picture. So actually I can do that. So this is the double-stranded DNA, and that's the stable version view.
Use it as a storage system. Is it stored as a pair, or is it stored as a single strand?
It's stored in this format because it's stable. It's harder to break. Okay.
It depends on, you have oligos which are single-stranded, and you have G blocks which are double-stranded. So you can order both.
You can get them built, fabricated, or so if you want, synthesized in this form or this form. Let's say it doesn't really matter. I'm saying from the point of view of the information, it's the same. Okay, but the one interesting thing that if you had the questions, why the GC content had to be 50%, and it has to do with the bonds between the 2 halves. And some pairs that A and T are bonded with 2 hydrogen bonds, so their stickiness is lower than the CG. So let's say the chemical reason or biochemical reason why we like to have 50% of G's and C's and 50% or around there is that then all the DNA strands with that balance will have a similar strength against being separated. And how to separate these? You just increase the temperature until these bonds break. And that's a bit of chemistry. And that's how PCR works. And I'm not going to explain PCR, but it generates many copies of PCR is amplifying the DNA. So it's kind of a nice way to generate huge amount of copies of your data if you want. So that's a bonus you get from storing data eventually in DNA. So again, as this morning, Ethan skipped the motivation why we want to store. Let's go down to the storage system and what really I thought about when I first saw this channel is okay, this must be can't be worse than a wireless channel, and let's see what we can do. But realize quickly that things don't work nicely in this type of channel. But the channel, I think we can just go quickly. You have binary data. You encode it into a sequence of ACTG nucleotides, and then you get it synthesized by many companies. Not many companies synthesize DNA, and it's expensive, but still affordable. It's maybe $100 to get one strand, let's say, in that order. Maybe more or less, and it could go down. The only limitation is the length. Producing length of strands of the order of 200 is affordable, and the longer you want them, the more expensive it becomes, and also it's because the yield is small, so you don't get as many. So you do lose on yield, and building long ones requires attaching together short ones. That process is tricky, and you don't get as many long ones in the end as you would like. So that's the writing process, is DNA synthesis. The storage channel, then that's made of two parts, we already said. The synthesis, which could have errors, and well, we'll take that. Then we order these DNA strands. We get back a little pot with the strands in it, and we can store that away, maybe in a fridge better. But there are other storage places you could put it in, and where the DNA will not degrade. By the way, if you leave it in the sun, it may die. I mean, it breaks. So you don't want to leave it out in the sun. Or even, I think, putting it in just water is also bad. It eventually degrades. So there are some chemicals you can put it in, embed it, and preserve it for a very long time. And then when you take this pot, which is your hard drive, if you want to read it. And to read it, you need this sequencing machine. The sequencing machine is something which extracts the sequence of ACTG, okay, some way. I'll focus on this box today. Of course, if you have done some kind of encoding here, then you will do your decoder based on these the sequences of ACTG. So you kind of have hard decoding problem here. And then you go back to the data once you do that hard decoding. The DNA sequencer, there are a few technologies doing that. So I will skip this slide. I think it was there. You don't need it. It's storage. It's the storage channel, and I think other people have talked about that before. But let's treat this as a communication channel. That was the idea. And we are focusing just on the sequencing as possibly the most error-prone operation compared to synthesis, which just is something important to have. It's being used enormously in all biochemical labs that do sequencing of natural DNA. So it is quite important that it's correct. So they do take care of making that very correct, avoiding as many errors as possible. As Aidan, I think, mentioned that 1 in 3,000, is that a recent quality? Anyway, it's relatively high quality writing, and reading is also high quality if you use this technology, which is Illumina sequencing, which is let's call it the classic technology, which is well established, but takes some hours of lab, like 5 hours the least is the process of sequencing. Okay, so that's not a great latency for a hard drive, but to read. So I won't show you this video because you can watch it yourself, how it works. It has a completely different technology than the one I will show you next, which is the Nanopore sequencing technology. And I think we can just start it from here. And I don't think it works from here. I'll change over to, or does it work? I don't know. I'll do that. So this is how the Nanopore sequencing works. It's more like a tape recorder. And when you listen to a tape, you have your tape going through the magnetic head, and you have your signal recorded on magnetic tape, and you listen to the music, okay, from old cassette recorders. The problem is that if you had any experience with tape recorders and cassette recorders, the quality of the music is degraded if the motor doesn't spin at a constant speed. You will have this wow and flutter effect on the quality of the music. So this sequencer scans the tape at a very random speed. It means it can have a huge variations in translocation of the tape through the reader. I'll show you this little video because it's kind of inspiring in understanding what type of channel you are looking at. Okay, so maybe I can even speed it up a bit and stop when.
It's not really doing it on the screen yet.
Sorry, I have to stop. I'll get there. Sorry, I should stop this here. Okay. Yeah, I knew it would not play there. Here it is. I'll start again. So this is the company is called Oxford Nanopore. It became commercial probably around 2015, 2016. And here is the machine. This is a USB size stick. You plug in a laptop. You put a sample in. Let me pause it there a minute. You put a sample. It's an array of pores, and samples magically go into a pore and then start pushing through. So you can see it here. This is one double strand. Let me pause it there. This pink thing is called the motor protein, which just clicks one nucleotide at a time and pushes it through. But the process by which this is happening is random. So how the true speed is controlled by this motor protein, which kind of behaves like it's eating some food and got enough energy and then clicks through one nucleotide. But since food is in this solution, you can think it's arriving randomly because of Brownian motion in this solution. So the actual time it takes for the motor protein to click and push the next base is very random, which ends up, if you think of from a communication system point of view, you're having symbol durations which have a very variable duration. So you have your variable duration by like many, could be maybe 2, 3, 4 times long from the fastest to the slowest case. So when you go there, so what happens when this DNA goes through? At the same time, there is in the solution you have some ions, and which are charged, so they flow through the pore together with the strand. That means that you can measure that current of ions with a collector at the bottom of the pore, and you can see the modulation of this current due to what's in the pore, because the different nucleotides in that strand will have different size. Just think of it as size. There are obviously many more other effects playing into this, but think of it as different balls of different size, and now you can, in that pore, which is like a pipe, you are clogging that pipe with a number of balls of different sizes, and you can infer the current by the set of balls that you have in this pore. So you can think of that as the state of the pore is which of the set of nucleotides you have in there, and you can use that current measure to go back and try to estimate your true sequence, and that's how that works. Okay, maybe any question on this video more but it's obviously this is you can't see it. We are talking about the diameter of that pore is like 2 nanometers. So it's, I don't think you can see it. This is not a true, it's a reconstructed video. I think it's amazing it works, but it does. And that sequencer produces, well, collects that current signal, converts it into the sequence of of nucleotides, and but with a lot more errors than the older sequencing device, Illumina sequencer. Okay, so we can stop that one and go back here. Stop music. Okay.
The Illumina sequencing workflow is composed of 4 basic steps: sample prep,
Hey.
cluster generation,
What's that?
sequencing,
Okay,
data analysis.
let's kill it. Now it's dead. Okay. So this is the picture is so that sequencer produces these current signals, measures these current signals. These are in the order of picoamps, so very, very low. And you can imagine your SNR problems you may have with such small currents. And from that, you have analog signal, and then you do the operation which is called in bioinformatics, it's called base calling, which is guessing what was the most likely sequence hidden into that read or into that squiggle.
Do you have access to the actual signal?
Yes, that's the beauty. So that machine gives you files of data, which are samples of that current signal. So we have, that's when I started liking this problem, because now I can do soft decoding because I have the actual physical signal. While if I'm taking the data after base calling, which is an operation provided by the sequencing devices, I don't see the physical signal anymore, so I cannot do soft decoding. So that was the one thing that I thought was interesting to exploit. So the whole thing especially the base calling is the one thing that is prone to insertion, deletions, and substitutions, because let's call it the demodulation. Maybe I can go to the next slide. First, you have the demodulator, which does this base calling operation, and that can go wrong, as it's the same as hard decision. And then you can have your hard decision decoder, which uses the discrete symbols and decode that. So that would be hard decoding. But given that we have access to the analog signals, when we can do soft decoding, and we open up to even design codes in the squiggle domain. And that was the game we thought we would like. Just as a note, the coding efficiency, if we want to see how good we are in this game, of course, at most you have 2 bits per nucleotide, given there's 4 variants. There may be possibilities of having more bases, more nucleotides, and of modified ones, which could provide you a bigger alphabet. Obviously, the squiggles will be harder to distinguish, but that's a possibility as well. But for now, 4 nucleotides distinct and 2 bits per nucleotide is kind of the best you could hope for. But we actually want to correct errors, so yes, you'll have, please.
You don't have to use a 4-letter alphabet.
You can, but the squiggles won't be as diverse.
You do it regularly now with methylated bases.
Yeah.
So you just have a methylated C or whatnot, and they're, again, nothing related to DNA storage, but they're doing it because of medical research. And nanopores can easily, now they claim at least, and we've seen something.
Yes. Yeah.
Extend the alphabet way beyond per nucleotide.
You can do it, but I think because of, we tried to produce some methylated sequences with methylation. First of all, you cannot amplify them. So you lose that methylation after it's PCR'd, and that's bad because then you can't make a copy of that data.
But you can have one strand if you are doing double-stranded, and for ONT you need double-stranded. Otherwise the helicase won't be able to serve as a motor that slows it down. Then you can have actually one strand that is the original one with methylations, and then the other one which is unmethylated, that one is amplified. So you lose a bit more when you read it, but it's...
The other thing is getting synthesized methylated is much more expensive. So we played with the basic, but definitely it's possible. But designing the code. So again, if you have the very good base caller that gives you the correct or enough correct hard decisions, probably yes.
We had a paper where we actually had 11.
Wow. Okay.
We had the only thing you have to take into account is mostly the charge of the symbols, because that's what's going to modulate the
squiggle.
Right, and 11 you can do a pretty good job. Just need to select them.
That's good. And in principle, we may have more symbols, and that would be a good benefit. Given that we have so much capacity in DNA, maybe that's something we will get there, as much as in wireless one day we may have 1024 QAM. Okay, that's the kind of parallel I would say. Okay, just the quick model, simplified model of the nanopore I was explaining to you. You have a number of bases in the pore that defines the state of the pore, and then for each set of bases that are in the pore, you will have a current level, but also you may have a duration. So here I'm sampling that signal, that current signal. It may have variable duration because of that motor protein working irregularly. So you can think of this, it's clearly a state machine. You move, one base comes in, you shift out the old one, and possibly the level changes. But it does matter that you hope that the level changes, but it doesn't necessarily change all the time. You may have some levels which are very close, and you may not see any jump between between the levels between two successive bases that come in. So then you don't know if you've been on a single level because of a long stretch of dwell time, or because there were two levels which were close to each other. So in a way, segmentation is really hard. You can't rely on trying to get the segmentation where things start and end. So where one nucleotide starts and the next one starts. So that's a very difficult synchronization problem.
Can you use a constraint code, say, to help you?
Yeah, you have to, you can design your code, and that's what we try to do, is to design codes that will avoid, for example, will always cause some jumps, for example. So you could look for, so in fact, you can see though, if you force the jumps to be larger than some threshold, then the rate goes down fast. So let's say if you want to avoid all sequences which don't jump more than your threshold, then you will give up rate just from the raw thing. But it's doable. That's the idea, is exactly to do that. But you can also give up on trying to force jumps and get a code that can also resolve situations where there's no jump, but you know the start and end, and you have a few symbols in between, as pretty much as the idea that you have to chop up your polar code into segments, and you need a comma. So what we do is actually put a comma in the squiggle domain as something very recognizable, and we use that as our Genie comma generating. Yeah.
So you can model it as a insertions and deletions channel, but I wanted to ask the question, is it actually like a little bit narrower, like it's a special subcase, because really all you can do isn't true.
Yeah.
The only kind of mistake that you can make is to have these repeats.
It's different. So it's not the insertion, deletion, substitution channel comes when you're dealing with the sequences of nucleotides. So let's say the hard decisions.
Yes.
So in that domain, but in the squiggle domain, when you're looking at the soft signal, there is no notion of insertion or deletion or substitution. There is only a signal that you are sampling fast enough to capture how it behaves. And then that analog signal is a signature, is a signature of what's the state of the pore. The difficult thing is to align the state of the pore to where you are on the squiggle. So that's where it's hard. But if you have a good reference starting point and a good reference ending point, in there you have squiggles, which you know where they start and where they end. You know you may have, I don't know, 10 nucleotides in there. Now the problem becomes doable. Although that squiggle could be long, many samples, or short. But you don't have the loss, you don't delete symbols, you don't delete bases. You just have that. So you can always try to find the best match of a squiggle to your code words in a code book.
It's no longer an insertion deletion channel.
Exactly. So that channel is kind of interesting by itself, because you can think of it as you have your sequence of states as of your nanopore, and then you have a duplication channel. You're just repeating the samples, stays on that level plus noise. So you can see it here. You just have for every state you have a level, and then you have many samples. So it's called this duplication channel, which has some statistics. I don't know, could be geometric or any uniform, whatever distribution you have there. And then you have all your noisy samples, and then you add your noise. So you add your noise, and that's what you see, sequence of samples. So in that sense, the IDS is not there anymore, okay? And so the good thing is that Oxford Nanopore released a software called Scrappy, which is a good emulator of how the nanopore behaves. So it gives you the actual levels, current levels, and you give it a sequence of bases, and you get your current levels. You generate your reference squiggle. It gives you the average amplitude and each point, and it gives you for each base, and it gives you the mean dwell time, duration, stretch, if you want. And then you can, and it gives you even the noise variance for each state. So that's kind of it was a good model to, if you didn't want to have, you don't have the machine to build to learn the model yourself. And we did actually use it because it was matching pretty well. So from the data, we could actually verify that the model from Scrappy was quite accurate until last year. They decided to change Pore, and they stopped releasing Scrappy. So now we are in a state where they only released the levels and nothing else. And the bad news is the old Pore was memory 5. That the state was made by 5 bases in the Pore, but now the new one has 9. That's the state is defined by 9 bases in the Pore. Now, if you count, that makes up a state machine with 250,000 or more states. So it gets pretty hard to think of it and even use it in an easy way. So so we took this channel anyway. This is an interesting channel by itself. So you can do try to estimate study mutual information, maybe capacity under constraint input as well. So because there are constraints, the homopolymer and GC are some of the constraints. But so as it is, that's the channel we are working on. And then we did try to build the sequence, build codes, right? And obviously it's brute force. Okay, we're building codes with a short number of bases. I think we work with short codes, and we have code books of 256 different squiggles that we can design. And in a way, we can select from all the possible sequences. I'll just jump over there. We're a bit short of time. I'll show you. So this is the kind of code we design. We concatenate a number of code words. We have the Gini spacer thing. So we put a known sequence there, which makes an easy detectable mark in the squiggle. So you can, with some reliability, find these places. When does it fail? When you see the squiggle pattern corresponding to this, if you find it in your code words. So you try to avoid having those commas appearing in your code words. So though you have to remove those, but eventually you end up with a pool of possible code words, and you want to pick the code book where you can maximize the difference between the squiggles. Okay? And that's an interesting thing because we found a way to compute the pairwise error probability between two squiggles, considering that you can have stretch and amplitude. And that's the picture of that. Maybe I can show you here. So you kind of want to have code words which have squiggles that don't look like this, because if you start from this one and you stretch it, you get that. start from this one, you stretch it, you get that, and they look terribly the same. And that's something you don't want. So we have a nice formula for computing the pairwise error probability between two squiggles under this random stretch. In that way, then we do a exhaustive search of among all possible code words. We have, and we pick the maximum click in a big graph, and then we picked our best code book in that way. So it's not very algebraic code construction. It's kind of messy, but the pairwise error expression helps to do that. And the good news is that it matches pretty well the data. So we designed our code books. We get them. We build those strands. These are 130 bases long. Well, we only use 100 bases for the data. The other part is needed for barcoding and for primers. But let's say the data is there. We actually get about 4 to 5 words, 4 to 5 code words in here, and they can be broken up, chopped, and each one of these is one of the 256 code words you have to search. So there is a way to measure the distance between code words, between the received squiggle, the noisy received squiggle, and the code words. It's kind of based to, it's the analog version of the edit distance. If you had, you kind of can compare two squiggles, and you can see if they match by under some stretch, and that's called the DT, dynamic time warping distance, which is equivalent to edit distance in discrete alphabet. By doing that, you can go for the closest code word to your received signal, which can have any stretch. If you've designed a good code book, all the code words are spread out enough, and they are recognizable. So to tell you the kind of how the performance of this thing, we can read one strand and get success rate 20–30%. So it's not great, but that's one read. Okay, now you read 5 or 10, and it's reliable enough to conclude that strand, or if you want that, this is for tagging. So that tag is actually in your system. Okay, so it's there and you have the non-counterfeit object by doing that. But this format can also be used for storage as well, because eventually these are all free, and you can, here we're using them as barcodes in terms of like tags for products, but otherwise they can be equally used as a storage system. Okay, as in terms of how many bits per nucleotide, around 1 bit per nucleotide in terms of efficiency. Given that you put all this in there, obviously with the new Nanopore, things have gone a bit lower, because it's this longer memory. We get only 4 code words in there. It's a bit worse, but given that there is a huge modeling error in general, the levels predicted by even Scrappy are on average correct, but let's say it's the variance in biology is massive. So I think we are spoiled by the Gaussian channel in general in our world. Okay, yeah, this is just examples of when we have concatenated. So we have also a better, we can decode one code word at a time by doing first segmentation, then decoding. we have a slightly better decoder, which jointly tries to decode even the commas, if you want, the separators, the spacers, and the code words. Now, all this can also be done with the neural network as well. So we have trained the neural network to do the decoding obviously much faster, because you just feed in the squiggle you pulled out after you found the comma, you feed in this signal, and the neural network does a pretty good job at classifying at basically equivalent to our minimum DTW distance decoder, and even better because the model we are using has model errors. So neural networks can generalize much better on that. So yeah, there are many decoders. You can imagine you can use, we actually use neural network even to find the spacers, and then for each letter in between, for each code word in between two spacers, we run another neural network doing the classifier. We have also barcodes, which are used as you can multiplex your reads in the sequencer. So you can put multiple samples in the sequencer. They all have their own different header barcode, and that's like another code that we have we design with the same criteria. We also read it as a squiggle, and we decode it, and that's useful if you want to read multiple tags from different products in one shot. So from the Nanopore sequencer. So these are the type of numbers I was showing you. This is the noise variance, the sigma. This is normal. We normalize all the squiggles to zero mean unit variance, and this is the standard deviation of the noise. So it's pretty high. I don't know if you think in SNR dB, maybe below 10 dB, between 5 to 10 dB, and here is the joint decoder error rates. The good news is that with that concatenation, it seems it's not, the comma is doing well, so that segmentation at the code word level is effective, so you don't have degradation by concatenating more. I would say now the limit is obviously the strand length, and so I have two, Adrian and Brandon have worked, one on the information theory questions, one on the code design and pairwise error probability. There's a few papers listed here, and we think it's still worth working on this for a bit more, and hope to hear feedback on that. Thank you.
The curves you're showing are Monte Carlo simulations?
Yes, these are.
How long does it take to do?
No, it's fast because you can. Sorry. This decoder is the complex decoder, the one that can do the joint decoder of spacers and the 4 different letters in the strand. So this is more complex. And in fact, I had here the complexity is here. This joint decoder needs to find the boundaries, the spacer, the commas, if you want, and then you have a number of samples. So this is N is the total number of samples, K is the word length, so how many bases in one coder here. That was maybe 10, and then you have the codebook size, 256, and how many code words I concatenate together. There is no other cross, but this way is complex. If you do the machine learning the neural network is instantaneous. And we train the neural network. We can train it first with the scrappy model, and then when we get data, we refine it. And so we do like transfer learning.
Actually get it from the machine, or
so we can do both. I mean, we first train the machine, the neural network with synthetic data. We know how to generate noise and stretch, which look like the real ones. That's from the model. But then obviously that we know that model is not accurate. So there's this idea of transfer learning, which means now we put in the real data for which we would run the slow decoder, learn the ground truth, and then train the neural network with that ground truth as well. So that always improves, because it learns all those mismatches between the model and the reality, which are sometimes annoyingly big. So that's the problem as well. Yeah, thanks.
So ONT provides you with the plethora of neural network models. Did you compare? Because they give you recurrent neural networks, convolutional combined with.
Yeah.
Why did you have to design your own neural networks?
Because it's too slow to run Dorado. This is their most recent base caller is like Dorado. It needs a GPU machine, and this is supposed to be a portable device, which eventually must go on a little smartphone maybe. But you cannot run your base caller that fast. So, and that's one reason. And the other reason is if you do one read with one base caller, it's got a lot of insertion deletion errors that we don't correct. So that's what the other side of the story.
Would you need a second stage after that first base caller and then to code your words? Is that the idea? Or because like when you do a base caller from the standard one, it gives you an ATGC sequence.
Yes.
You have words that are longer. So
we eventually almost don't care what these are squiggles, and we have a squiggled book. It's like coded modulation, if you want.
You wanted to, if I give you a raw sequence, you'd want it to code it back to a set of squiggles, right?
Yeah.
So you'd have a second stage to put it into, right? If somebody just gave you the.
No. Every single each one of these between two commas, I have a code book. I have one code word, and that is just a classic neural network classifier. I just have a code book with 256 code words, so I know a kind of the center point of the cluster from the model of the squiggles, and then I try to find the closest reference code word in the code book to the received one, which is stretched and noisy.
So just to add to that,
Yes.
you did that same thing with the chemically modified DNA with the larger alphabet.
Yeah.
It's exactly the same idea. You actually classify k-mers, in our case, formers, and for that you design specialized neural networks.
Yes.
So your neural network is designed to classify the squiggles, as you call them.
Yes.
Not individual symbols.
Not individual symbol. Yeah.
That makes it faster, basically.
Yes, definitely yes.
In,
Otherwise, you've made a base caller. I mean, if you design a generic base caller, but this you can make it faster, and then I think we control the error probability of the code book we design. That's the other thing we have control of. But definitely, I think if I could give you this code book and you run it on your network and you can compare.
The issue is because the words are long. You have a difficult classification task. Maybe it would have made sense to break down. We did k-mers, K is 4, and it already started to degrade in terms of the performance with very sophisticated neural networks. So it makes sense to break it up into smaller, like sub-squiggles for classification purposes.
Our neural network is trivial, like it's 3 layers and
Just 3 layers?
Yeah, 3-layer convolution and 1 fully connected. Just 2 or 3 CNN. Stride, maybe it's input samples. I think strides maybe. The kernel size maybe 8 to to 16 samples input. But the neural network is basically dummy neural network. It's not advanced. I'm sure the base caller is much more advanced because it has to deal with the sliding window. So that's a massive, much more complex. It's mostly almost a match filter. It's barely a neural network, I would say.
All right. Thank you.
Thank you.